Okay, let's work an example. This is going to be a Rankine cycle that incorporates reheat between two turbines, and we're also going to include isentropic efficiencies in the turbine and the pump. I believe this is modeled after problem 830 in your heat transfer textbook, and that builds off problem 829, just FYI. Okay. So our steam generator is a control volume device. That's where we're bringing in thermal energy through rate of heat transfer from some hot source. Our pump is also a control volume device. It's increasing the pressure of the fluid, and to do that we have to provide a rate of work input. The condenser is a heat transfer device by which we take energy out of the fluid through heat transfer to the surroundings. And then my turbines are work devices that use the energy of the fluid to produce rate of work power on a shaft. Okay, let's use the values given in problem 830. And let's try and draw a TS diagram to better understand what we've got going on here. I'm going to try and draw it nice and large. There's entropy on the x-axis. There's temperature on the y-axis. And let's get a vapor dome up here. Need it to be nice and large. I think drawing it with a fat tail is going to help me here. At least I think so. Okay, let's start with the pump at state 5 because I know I'm a saturated liquid and I'm at the lowest pressure, the condenser pressure, at that point in the cycle. Okay, so here is state 5. And the pump is going to pump the fluid to a higher pressure level, so up to a larger ISO bar. I'm going to label this state 6. And now I'm at my high pressure between state 6 and 1, passing through the boiler or the steam generator. So I'm going to follow this high pressure ISO bar. And the problem says this is at 100 bar. So the pressure here on this ISO bar is 100 bar pressure. And I go up to state 1. And state 1, the problem tells me, is at 480 Celsius. Okay. So I am at the inlet now to my first turbine, my high pressure turbine. And I operate, or I take energy out of the fluid to produce work, and that drops me down to an intermediate state. I'm going to call that 2, and this is at an intermediate pressure, and the problem specifies this as 7 bar, I believe. So this is a lower ISO bar, 7 bar. Now from the exit of turbine 1, I pass back into my steam generator and I reheat. So I'm going to follow this ISO bar. So it's at a lower quality at state 2. I heat until it's completely saturated vapor, and then I follow the 7 bar ISO bar into the superheated region, and I stop at state 3, which the problem says is also at 480 degrees Celsius. And then at this point, I go through turbine 2 and expand the fluid down to my condenser pressure, which is state 4. And this ISO bar is at 0.06 bar pressure. Okay, now let's include the effect of isentropic efficiencies on the turbines and the pump. So what is that going to do for us? I'll switch to another color. So the pump, in reality, you have to overcome irreversibilities such as friction, heat transfer. And that means the pump is going to pump between 0.06 bar and 100 bar, but state 6 is going to be at a higher entropy level. So this actually becomes state 6s, the isentropic state, and this becomes state 6, the real state 6. And because of the irreversibilities, I no longer know the path, so I illustrate that with a dotted line between state 5 and 6. Okay, let's look at the turbine. The turbine experiences irreversibilities, things like friction on all the seals and bearings, heat transfer from the casing. So state 2 here is actually state 2s, the isentropic output of the turbine. And then in reality, I'm at the same intermediate pressure, but at a higher entropy. And to indicate the irreversible nature of this, I don't know the path, so I do a dotted line. And then yet again the same thing for the second turbine, state 3 to 4. Well, this isentropic becomes state 4s, and then at the same pressure, this is now state 4 real. And I draw the dotted line. Now at this point, I don't know that state 2s or 2 is in the two-phase region. I also don't know that state 4s and 4 are in the two-phase region. So I've drawn with a little bit of foreknowledge here. It could be that your analysis shows in one of these it's in the superheated region, and that's okay. You just update as you have new information. But I think this is enough to get us started.